Okay, so welcome back to another video. So this time we're given a function f of x equals x squared divided by 2x minus 1. So now the question being asked is, what is f superscript n of x? Don't be confused with this one. The n is not defined as the derivative, like the nth derivative and so on. This is known at, we're being asked is to find a generalized formula for the nth iterate formula. And what is an nth iterate formula? The standard definition it's defined for nth derivative formula is when we're given our function f, it's actually equal to f, compose f, so on and so forth, f of x, where within our functions f, it's being composed n times. So basically it's a composition of another composition of so forth of the same function n number of times. So that's today's video. We're going to be finding a generalized formula for our function f. So with that, let's get started. Let's actually work off the first case. So we know that if we were to plug 1 into here, so f1 of x is just basically the same function given. So we know that for sure. So I can also just write here, this is f1 of x. That's a 1, not a prime. And then now let's evaluate f2 of x. So this means we have f compose f of x, which this is equal to, so we just plug in our f of x, x squared divided by 2x minus 1, and just put in with the same function in for our input for f, the second f I mean. So this means, to put it this way, I can actually just move the x squared as outside and write it as a product in a sense. So this means we have x squared divided by 2x minus 1 square, then multiply by 2, then x squared minus 2x minus 1, and then minus 1, and then and the numerator is 1. And so therefore when we simplify this out, then we get x to the 4th divided by 2x minus 1 square, then multiply by, okay, so I can just distribute, but also, let's also do this so that way we can get a common denominator. So this would mean, actually, the parentheses is supposed to be, whoopsies. Parentheses is supposed to be here, and then subtract 1. Okay, there you go. Now it would make things a lot easier to do. So that means get a common denominator. So that would have to mean, if I distribute the 2, then that means common denominator will be 2x minus 1. So let's do that. So we have 2x minus 1, and then minus 2x minus 1. So then I can just cross multiply. So this is 2x minus 1 here. So we get that in negative 1, and then 2x squared. Okay, and then multiply by 1. And then that's equal to, we simplify this entire thing out, we get 2x minus 1, then multiply by 2x squared minus 2x, and then plus 1. Just notice that one of the quantities for 2x minus 1 would cancel the denominator, so we're just left with 2x minus 1 with this just one quantity, and then multiply by here. Okay. So far that's our f2 of x. So now let's actually calculate f3 of x. So right here, and you get how this works. So it's f compose f, but I can write f2 compose with f of x. So here, you know what? Just for the sake of it, I'll write it anyway. So 2 compose f, and then x, which that's equal to, so that means our f of 2 of x is here, so I can just put our x squared over 2x minus 1 into here. So I can write this in terms of products. So that means let's see, x squared divided by 2x minus 1 to the fourth, multiplied by, I can also write this also with products too, so it's 1 divided by this product, and then multiply by 1 divided by this product, rather the polynomial in particular. So this means 2, and then x squared divided by 2x minus 1 times 1, then multiplied by 2 x squared divided by 2x minus 1 square minus 2 times x squared divided by 2x minus 1, then minus 1. It's 1. Okay, now let's actually simplify this out, but also later with this step, I'm just going to get find a common denominator. So this is x to the 8th divided by 2x minus 1 to the 4th. And then that's multiplied by this is the same thing as where is it? Right here. So I can just use the same steps with that same when trying to show my work. So that means 2x squared divided by 2x minus 1, then minus 2x minus 1 divided by 2x minus 1, all divided by 1. And then for this piece, just because it's square, so that means our common denominator will have to be 2x minus 1 and then square. So this one should be 2x minus 1 square, then minus 2x square multiplied by 2x minus 1 divided by, same thing, 2x minus 1 square. Yeah, it's supposed to be plus. I don't know why I wrote minus here. That's a plus over here. Okay. And then it's supposed to be plus 2x minus 1 squared divided by 2x minus 1 square. All this being with the numerator of 1. If we simplify all this out, I'm not gonna show the rest of the work. You can actually verify this yourself if you want, but it should come down that f3 of x is equal to, see, denominator is 2x minus 1, then multiply by 2x squared minus 2x plus 1, okay, and then 2x4 minus 4x cubed plus 6x squared. Notice that the numbers here is kind of like forming from Pascal's triangle, and then plus 1. Specifically looking at the constants. So all this is 1. So let's also note that I can actually rewrite the terms as well. So 2x minus 1 is equal to x plus x minus 1, okay? Then 2x squared minus 2x plus 1, that's equal to x squared, then plus, and then I can just factor out, or even though subtracting the x squared, but this also factor out to a perfect square, so this is x minus 1 squared, and then 2x4 minus 4x cubed plus 6x squared minus 4x plus 1, that's equal to x to the 4th, then plus x minus 1 to the 4th as well. So with that, now we can rewrite our terms. So I'm pretty sure I got room to fit this space. Yes, I do. Okay, so we have that f1 of x is equal to x squared divided by x plus x minus 1, okay? And I'm gonna underline this in red after writing these three terms out first, just so we can come up with some formulation. Then f of 2x, so that means this is x plus x minus 1, and then x squared plus x minus 1 square all over x to the 4th. f3 of x is equal to, okay, right? We write the same denominator as before, so x plus x minus 1 multiply x square plus x minus 1 square, then multiply by okay, x fourth plus x minus 1 to the 4th. And then this is x to the 8th. Okay, so far, we bend this down. Okay, for a sec. So we can see that we have our three formulas, F1, F2, and then F3. I'm just bending down a bit because you slightly cut off the F3 just for a tiny bit, but then it'll be fine. Now we can actually come up with a standard formulation on for each n greater than or equal to 1. So we can take it. So we can actually take a guess and see that. I'll write it over here. That Fn of x is equal to x to the power 2 with the power of n, and then that's being multiplied by the product series from k is equal to 0 to m minus 1 of okay, in another bracket, so x to the 2 power k, and then plus x minus 1 with the power 2 to the k power. Okay, and then next, and then to the negative 1. So that's our formulation. Let me underline our formulation. So this is right here. I'll even box it just for the sake of it, just so you guys can see. Yeah, so we have our F1 here, F2 here, and then F3 over here. If you can see the red line, like right there. Yeah. In fact, let me just zoom this out just a tiny bit. Okay, should be fine with this. Yeah, right there should be good. So we have our possible general formulation for f of n of x equals this, but how do we know for sure that this general formulation that we come up with works for every single natural number 1? So it's pretty neat, because in order to show that, we're actually going to have to prove by induction. Now I actually made a video on proving using mathematical induction over a year ago, so you can actually check out that video if you want to. I'll leave a link to that video in the description. But basically, what induction says is, in order to prove that a formula for a formula to work, you need to show 3 different cases. One, that the base case is as for natural number n is equal to 1, that holds. The second is you have to assume that show that n is true, and then also the third step is you need to show that n plus 1 is true. So one step iterated to show that it holds for every single natural number. So that's what we're gonna do. We're gonna prove by induction to show that this in fact is possibly our formulation for given this function here. So first step is base case. Well, I don't even need to write the work, because we just need to show that n is equal to 1 works, which we did, which it's already obvious to see that if n is equal to 1, if you plug everything for 1, it's let's see, 0, and then you're just gonna get the same thing as our given f of x, so that holds. Nice. So now let's assume that it is true for true that n is equal to m for all where m is actually for all positive integers. If we assume that m is true, then we have to show that n plus 1 is true in order for it to satisfy. So that means when we plug, let's see, f of n, let's see, I'm gonna put it right over here. Let's see, f of m is equal to f of m is equal to x to power m, then the whole product series again. Then that's supposed to be n minus 1. That's supposed to be n over here, by the way. I accidentally wrote an n. So n, and then let's see, so n minus 1, then k is equal to 0 of the same thing. So x to k plus x minus 1 to k, and then negative 1. Okay, nice. So we have that. So now let's actually show that n plus 1 is true. So when we do that, so that would have to mean f of n plus 1 is defined as is equal to f of m, then composed with f of x. Okay, so that means we take our f of m function and then plug in our f of x for our input. So this means, I'm just gonna write it over here. So that means, okay, this is gonna be a long one. So x squared divided by 2x minus 1, then 2 to the power with 2 to the power n. Okay, and x is still the same. So n minus 1, k is equals 0 of x squared divided by 2x minus 1, 2 to the power k, then plus, and 2 to the power k, and then with the negative exponent, negative 1. Okay, so yeah, we just plug in our f of x function into as a composition with our f of m, which is here. So we get this formulation. So now, next what I want to do is I want to multiply, so let me write this in red. And this is actually going to preserve the equation. So over here, multiply 2x minus 1 divided by 2x minus 1, and then with the power of 2 to the m, and then minus 1. Yeah, so that way it's still equal to 1 if you just cancel the terms out. So like I said, the equation still preserves. So that means, here, let's put it this way. I'll even m minus 1. Okay, nice. Now going back to the brown. When we do that, so notice that we can actually simplify this out, specifically when we focus on these two terms of the product. So 2m minus 1, 2m over here. If you were to distribute the 2m, so we can actually simplify this out just a bit. So when we do this, so this is 2 times 2 to the m. So this means this is x to the power 2 to the power of m plus 1. And then when you distribute 2 to the m, so this is over here, so you can rewrite this as the minus, so 2x minus 1 with the power of negative 2m to the power. You subtract that, that cancels, and then you're left with the negative 1, so that's kind of the inverse, so that means you're still left with 2x minus 1 in the denominator. Okay, and then yeah, we're just still rewriting the same product in here like before. So I'm still in the negative 1, and then multiply by 1 divided by, and then you just distribute. So this is under the denominator. So 2x minus 1, 2, like so. So now let's also pay attention. Now let's actually note something over here. I think I can write under this light, should be fine. So I'm going back to the red marker again. Notice that 2 to the m minus, yeah, to the minus 1, actually, not under the exponent, it's supposed to be over here. Minus 1. So notice that that's actually equal to our summation of from infinity to, well, actually not infinity, sorry. It's supposed to be m minus 1. This is a partial sum. minus 1 to k is equal to 0. So notice that that's going to equal to 2n minus 1 multiplied by, or not multiply, plus, this is a summation, my bad, minus 2, then plus dot 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 so on to 2 to the 0. So then what that means is we can actually rewrite this as a, we can rewrite this piece in terms of, well, okay, so let me just back up a bit, sorry about that. 2 to the n minus 1 is equal to the summation, which is equal to our series here from k is equal to 0 to n minus 1. So we can replace our series for here, and then notice that we can actually use our rules for exponents and then multiply it as with products. So this means this is 2 to the x minus 1, 2 to the m minus 1, then multiply by 1, and then 2 to the x minus 1, 2 to the m minus 1. Okay, good. You can still see that? Yeah, you can still see that, right? Right over here. Yeah. Okay, so that means we can just replace this. Then when we actually rewrite it, we can rewrite this as a product. So n minus 1, that's our upper index, and then k is equal to 0 of 2 to the x minus 1. Then the power is 2 to the k, 2 to the power k, and then inverse negative 1. Okay, so now let's rewrite this again. Minus 1, then 2 to the power k, and then negative 1. Okay, nice. That was a long one, I apologize for that. Now, this means, let's see, we multiply that, then let's actually distribute our powers into both the numerators and denominators. So rewrite this again. Well, actually, probably have to write small, but I'll try the best I can. So 2x minus 1, and then let's see, so pi, or product rather, n minus 1, k is equal to 0. Okay, then we can distribute the power, so that means this is x to the 2k, let's see, yeah, 2k plus 1. Yeah, actually, rather, I don't have to simplify this out. I can actually just keep it as x squared, and then raise to the power 2k. And then same thing, so, but this one, like, I want to get a common denominator. So this would have to be, if I simplify this out, I get x squared, and then I think it's minus 2x plus 1, yeah. Minus 2x plus 1, then its power is 2 to the power k, all divided by, yeah, 2 to the x minus 1, and 2 to the power of k. And then we can close these brackets off. Negative 1, and then multiply with our product. So pi minus 1, k is equal to 0. 2x minus 1, 2 to the power k, and then negative 1. Okay, nice. I apologize that took like a long time. So, okay, so now with the product series we can multiply it through, because not only that, they also share the same index from k is equal to 0 to n minus 1. But notice that if I take its inverse, if I were to, let's say, multiply the exponent, the negative 1 distributed to here, so this is negative 1, so that means this can be flipped to the numerator. Same thing over here, but this is flipped to the denominator. Notice that we're actually going to cancel out some terms. Specifically, we're going to cancel the denominator. So not only will this product series disappear, so will the denominators inside this product series here. So now back to here, we have x to the 2m to the power 2m plus n plus 1, then divide by 2x minus 1, okay, and then multiply by the power from m, or k is equal to 0 to m minus 1, and then all you're left with is just the numerator. So this is, okay, cool, and then to the -1. Don't forget about that. Okay, just like from I did earlier, now we can actually simplify this out. Now we can multiply our exponents from here using the exponent rules. So, okay, same as before, 2m plus 1, then divide by 2x minus 1, multiply by the product series, k is equal to 0, m minus 1, and then, so this is, when you multiply exponents, it's 2 times 2 to the k plus 1, or 2 to the k, when really, when you combine them together, you're gonna get x to the 2 power k plus 1. Now this is actually a perfect square here, so I can just write this as x minus 1. But there's a 2, so that means this will be in powers of 2, so this is also will be 2 to the power k plus 1. Yep. And then, okay. And -1, don't forget. So that. And now we have this. Now let's actually change our index up a bit. So now let's actually let our index start at k is equal to 1. So we're just changing our indexes, but we're still getting the same equation anyway. So 2, then power m plus 1, then divided by 2x minus 1, multiplied by product. So we're going to let our starting index be k is equal to 1. So that would have to mean our new upper index will have to be just m. So this means we have x to the, let me write in parentheses, to the k, and then plus x minus 1, and then this is just 2 to the k. Yeah, it's just 2 to the k, and then to the -1. Okay. Wow, that was very exhausting. Okay, so now notice that, oops, let me write this in red too. So notice that 1 over 2, here, let me write note. So note that 1 over 2x minus 1 can also be rewritten as, we can just use the power series, well, but let's start at k is equal to 0. So this is, so x to the 2 raised to the 0, then plus x minus 1, 2 to the 0, and then minus 1. Okay, so notice that 1 over 2x minus 1 is equal to 2x raised to the 2 with the power 0, and then plus x minus 1. This is just from our same series, but we're just going to let k is equal to 0. So notice with that, what this means is we can actually manipulate our equation. So this means the 1 over 2x minus 1 over here, we can actually move it to the inside and rearrange the product series again. So we'll be also changing our index again. So this would mean that, oops. So this would mean we would have x to the power 2 to the power m plus 1, then multiply by our product series. Now we can say, now we can rewrite this and put k is equal to 0, and our upper index is m minus 1, with x to the 2k, or to the 2 to the power k, then plus x minus 1, and then 2 to the power k, and since n is equal to m, which we assume that's true, then my bad, this is actually supposed to be an m right here, my bad. Oh, I'm really screwed up, but it's whatever. So this is supposed to be m over here. Okay, now everything makes sense. So since we said that n equals m, we assume that's true, and we want to show that n plus 1 is true as well. Well, if you were to plug n plus 1 into here, it matches exactly like our formulation. You plug n plus 1 goes here, and then n plus 1, you plug it into here, so it's n plus 1 minus 1, which is m with the upper index, and the same formulation. So we have just shown by induction that that this formula holds true for all natural numbers, n greater than or equal to 1, or you could say positive for all positive integers. So we are done. We proved all three cases. We just proved that f for our base, by induction, the base case works, which you give them the same function. We assume m is true. To be sure that n is true, then we have to show that n plus 1 is true, which we just did. So that means from the previous iteration, then n is true. So then everything is true by induction, holds all cases. So therefore, with our conclusion, f sub n of x is equal to x to the power 2 with the power n, and then multiply our product series. So this is n minus 1 to k is equal 0 of x to the power k plus x minus 1, 2 to the power k, and then with raised to the negative 1. So this is our formula such that f of x equals x squared divided by 2x minus 1, like so. All right, that's gonna be a lot of editing, but that's a lot of work, and I hope you enjoy. Sweet.